ammonia reactor. So both enters at high pressure, almost 140 bar pressure, and a temperature of 450 Kelvin. Introduced into this ammonia reactor. Typical ammonia reactor is like a plug flow reactor. In the ammonia reactor, in the urea reactor, ammonia reacts with carbon dioxide, forms ammonium carbamate. Ammonium carbamate further converts to urea and water. So, typical conversion we can achieve in urea reactors is around 70%. So 30% of reactants, 30% of the stream leaving from the urea reactor will be unconverted reactants, predominantly ammonia, CO2 and ammonium carbamate. So we have to separate these unreacted reactants from the urea. So unreacted reactants are ammonia, CO2 and urea. And we know that how do we separate? A simple principle. We know that urea at atmospheric pressure, at atmospheric temperature will be in the solid form. Whereas ammonium carbamate, ammonia, CO2, they will exist as a gaseous form at atmospheric pressure, atmospheric temperature. Sorry, ammonia and CO2 exist as a gaseous form at atmospheric pressure and atmospheric temperature. Even if, although ammonium carbamate can exist in the liquid form, but that will decompose very fast. That will decompose very fast into ammonia and CO2. So that's why immediately after leaving the urea reactor, the product stream undergoes through pressure reducing process. Side by side heating. Why we have to heat? Urea at the atmospheric pressure, at atmospheric temperature, it will be in the solid form. We wanted to make sure it is in liquid form for the transportation purpose. So there will be intermediate heating while reducing the pressure. So first we will use expansion valve in the gradual reduction of the pressure. The reason for the gradual reduction of the pressure is if you suddenly release the pressure or suddenly compress it, ammonium carbamate can form as a crystals. So that can, ammonium carbamate crystals can be a dangerous thing. So that's why the pressure will be released very gradually from 140 bar to 20 bar, then heated, then again released to 1 bar pressure. So finally we get urea solution. The urea solution has water. So we wanted to make it concentrated like a molten salt. So we have here the evaporator, vacuum evaporator. This is the evaporator, vacuum evaporator. So this vacuum evaporator, you will definitely see in, you might have learned about this evaporation process either in heat transfer course or process equipment design. So just typical heat exchanger with vacuum applied, that is the vacuum evaporator. So usually this vacuum evaporator operates at 660 centimeters of mercury vacuum. So after this evaporation, you will get the molten tank. Then it introduced into the drilling tower. I have explained in the last class. Typical drilling tower looks like a shower of liquid, like a shower what we use, like the spray jet. Through the spray jet, small droplets of urea liquid droplets will fall from the bottom. The air is supplied, and heat transfer between cold air and hot urea solution, urea droplet heat transfer takes place, and solidification of urea granules will take place. That way you get the urea granules. Now what we have is ammonia, CO2, ammonia and CO2. These are the unreacted reactants. These needs to be recycled. Remember that we have reduced the pressure, and the pressure here is 1 atmosphere or between 1 to 20 atmospheric pressure. The gaseous pressure here is 1 to 20. because some of the gas is coming at 20 bar here, some of the gas is coming at 1 bar here, so it would be intermediate pressure. Whereas we are supplying ammonia here and CO2 here is almost at 140 bar pressure. 140 bar pressure. So before we recycle them, we need to compress it because we need to make sure both are at same pressure before we introduce. So we need to compress it. So if you compress it, what will happen is, if you suddenly compress it or suddenly release the pressure, the ammonium carbamate, the carbamate will tend to form, or the liquid suppose instead of the ammonia CO2 reaction will happen, carbamate will form and carbamate crystals can form. The carbamate crystals can form. In any compressor, compressor means what? You are basically pushing the gas at very high pressure. If you have any crystals, two things can happen. Abrasion between the crystals and the surface will happen, and also the ammonium carbamate crystals can be highly corrosive. So because of that, straight away we will not be able to recycle. We will not be able to recycle, or we cannot recycle as such. Compress it and recycle it. So in the old urea industries, they used to find a way to utilize this ammonia and CO2 rather than recycling it. In the modern industries, so that's why the typical old process are once throughput process. Once throughput process means unreacted reactants are not able to recycle back. Once throughput only. So some of the industries and the old industries used to just utilize the ammonia and CO2 for some other purpose instead of recycling back. But in the modern industries, they have developed a different technique to recycle this ammonia and CO2. So what is this way? So when you when you compress it, the reaction between ammonia and CO2 will happen, and some amount of carbamate will form. When you recycle it, we have ammonia and CO2, and some amount of ammonia reacts with some amount of CO2 can form the carbamate. Now let's take a simple phenomena here. Suppose we have ammonia, we have CO2, and we have carbamate. We have ammonia and we have CO2 and we have carbamate, and we know this is a reversible reaction. Reversible reactions means at any instance all the three components will form, and there is a highly possibility of the chemical reaction equilibrium can happen. There is a highly possibility, or always happens, therefore chemical reaction equilibrium. So if you have ammonia, CO2, or even though ammonia and CO2 reacts and forms carbamate, ammonia and CO2 will not completely convert because this is a reversible reaction. Some amount of carbamate decomposes back. So at equilibrium state, you have ammonia, you have CO2, and you have carbamate. At equilibrium means what? This concentration, after retaining the equilibrium, the concentration of ammonia, the concentration of CO2, and the concentration of carbamate will be remain constant, right? Although there is a reaction happens between ammonia and CO2, because of this recycle reaction, so reversible reaction, there is a equilibrium state exists at some point of time. What point of time we call it as equilibrium? After that point of time, the concentration of ammonia, the concentration of CO2, and the concentration of carbamate will remain constant. Suppose if I remove some amount of ammonia from this, let's say if I remove, we have an equilibrium condition, and at equilibrium condition we have some concentration of CO2, some concentration of ammonia, and some concentration of carbamate. All are the concentrations. Let's say from this equilibrium I have removed some amount of ammonia. I have disturbed the equilibrium. I have removed some amount of ammonia. I have disturbed the equilibrium. What will happen? Can any guess from the students? What will happen? I have an equilibrium mixture. I have disturbed the equilibrium. How have I disturbed? I have removed some of the ammonia from this, what will happen? Any student, any guess from the students? Please think about it. Please think about it. If I disturb the equilibrium, will the system will again want to reach the equilibrium or not? If I disturb the equilibrium, will the system again wants to come back to the equilibrium state or not? Because I haven't changed the temperature pressure. So these two are remains same. Temperature pressure remains same. If I disturb the equilibrium, will the system wants to come back to the equilibrium or not? Can that be answered by anyone?
Yes, sir, it will come in equilibrium.
Yes. So what should happen? So to come to equilibrium state, what should happen? The concentration of ammonia should increase from the reduced value to the previous value or not?
The carbamate concentration will decrease and the concentration of ammonia will increase and CO2 also.
Very good. That is the perfect answer. So if I remove some amount of ammonia, the system again wants to come back to the equilibrium. So since CO2 concentration remains same, the carbamate has to decompose into ammonia and CO2. The carbamate has to decompose into ammonia and CO2. That way, to increase the concentration of ammonia, the carbamate has to decompose again to reach the equilibrium state. Thank you. Uh, so if I remove some amount of ammonia, the carbamate decomposition will happen. Equilibrium gets disturbed and leads to the decomposition of carbamate. So how do we remove this ammonia? How do we remove the ammonia? We can strip ammonia with help of CO2. We can strip ammonia with help of CO2. Suppose we have a gases. Suppose we have a gases where ammonia is only present. Suppose we have ammonia and CO2. If I do the stripping process, with the help of a liquid CO2, these are the gas and these are the gas. And if I pass liquid CO2 through this, ammonia tend to react. Since ammonia reacts with CO2 very fast, it will tend to absorb. It will tend to absorb into this one very faster. It will tend to absorb into this system very faster. That way, with help of CO2, we can do this stripping. So if I have an equilibrium mixture of ammonia, CO2 and carbamate, if I just pass through some liquid CO2 through this, then I can extract some of the ammonia from here. I can remove some of the ammonia from here. That way, the carbamate decomposes back. So the modern processes you just like this. The typical modern process follows this route. Ammonia will be supplied in excess. That way, they can make sure that complete conversion of CO2 takes place in the urea reaction. That way, the complete conversion of CO2 will take place in the urea reaction. In the modern industries, they will supply excess amount of ammonia than the stoichiometrically required. So the CO2 will become limiting reactant. So when you supply one in excess and CO2 in the limiting reactant, even though you have the 70% conversion, you can almost consume whatever amount of CO2 available there. So ammonia, let's say the CO2 is completely consumed. Then we have ammonia and water, urea and carbamate in the urea reactor leaving stream, because CO2 is completely consumed. So basically we are supplying less than stoichiometric liquefied CO2 so that we can consume complete CO2. So, so in the stream leaving the urea reactor will have ammonia, water, urea and carbamate. Now here it is passed, it goes to the stripper. So in the stripper we will basically supply the CO2. Basically we supply the CO2. The CO2 takes whatever ammonia is present. The CO2 takes whatever ammonia is present. As ammonia going, the carbamate further decomposes. As ammonia transferring, the carbamate further decomposes. That way, when the stream leaving the stripper will have only ammonia and CO2. Will have only ammonia and CO2. So this is ammonia gas, and here we have ammonia CO2 gas. Then the reaction, the mixes with the reactant and goes to the carbamate condenser, again recycle back. This way, the complete utilization of ammonia takes place. The complete utilization of ammonia takes place. That way, we get the urea solution out, and all the unreacted reactants goes back. So how do we achieve this stripping and reaction followed? So in the modern industries, they use this type of reactor followed by a stripper, reactor followed by a stripping section. So here the reactor, this is the reactor, this is the reactor, this is the reactor, and typical like heat exchanger type stripping section will be used. Heat exchanger type stripping section will be used, and you can see the liquid the liquid flows like a just falling film, just flows like a film. The liquid, this is the tube, this is the tube. Liquid just flows like a film, liquid just flows like a film, and the gases pass through this, the gases pass through this. That way we can achieve more amount of mass transfer through this one. So this is like a typical falling film evaporator. If you see any evaporator, that's called falling film evaporator. Falling film evaporator. Falling film evaporator. So this urea reactor looks like a falling film evaporator. So in the evaporator we have a free space and we have a heat exchanger. But in this is used as a reactor. The free space is used as a reactor, and heat exchanger part is used as a stripper. That way they're able to achieve the reaction immediately followed by the stripping, because we need to maintain the reaction and stripping at same pressure. We need to carry out the reaction and stripping at the same pressure. That's why they join both. They join both. I hope you're able to understand, but if you get any doubt, please ask me. I'm happy to answer. This is another type of reactor where they join reactor and stripper, and here we have a reactor separately and we have the stripper separately. So this is another design of urea reactor followed by the stripping section they can use. So that's the way we can achieve the complete conversion of ammonia in the urea reactor by supplying excess ammonia and by stripping with CO2. So that way we're able to completely consume all the reactants. So most of the modern industries follow this route. Most of the modern industries follow this route. But however, there are some still industries we're still using the one throughput process. Still they're using the one throughput process, but very less, very less. Most of the industries follow this technology to complete conversion of reactants. So that's all about urea process. So I have discussed what is the process, what is the thermodynamics, what is the old industries looks like, and what is the modern industries looks like, and how to achieve that equilibrium. So please go through this, and please also read the textbook which I have given. So if you get any doubt, I'll be very happy to answer your doubts. So I'll just wait for a few seconds. If you have any questions, I can answer. Otherwise, I'll move to next topic. Students, if you have any questions on the urea process, you may ask me. Otherwise, I'll move to the next process. I hope I'm giving some information which giving you some excitement or something that you are learning. This will be really helpful if you visit any process industries or if you work in industries. Some of the details I'm giving. Also, I'm telling you why we are studying mass transfer, why we are studying reaction engineering, why we are studying heat transfer, why we are studying mechanical operations. I'm trying, you can see all the process involved, all these core subjects, and these are very, very important subjects. And all the industries uses these processes. So I assume that none of your questions. So I'll move to the next topic. So today we'll talk about the next topic is production of nitric acid. This is another important chemical which is used in most of the industries, especially fertilizer industries. Fertilizer industries uses nitric acid. Nitric acid was initially produced, that is around Second World War time. They produced from the saltpeter and chili saltpeter, that is from the potassium nitrate and sodium nitrate. Initially, nitric acid was produced from these two. These two are available in the directly available in the undergrounds. So if they used to mine these raw materials and they used to react with sulfuric acid to produce nitric acid. Saltpeter or chili saltpeter is used to produce the nitric acid, and these two are directly available as a raw materials in the underground. So they used to mine these materials and they used to react with sulfuric acid to produce the nitric acid. Typical reaction, typical reaction. The sodium nitrate react with sulfuric acid and produces nitric acid. That is the very, very simple reaction. But with the invention or with the rapid development of hydrocarbons, that is rapid invention on the hydrocarbon productions, the amount of ammonia produced has also increased. Amount of ammonia produced also increased. At the same time, the sources for these nitrates also reduced. As upon the invention of hydrocarbons, ammonia production has increased greatly because most of the hydrocarbons do contain nitrogen, nitrogen as a some of the what called inert material. So that whatever nitrogen is there in the hydrocarbons, they is utilized for the ammonia production process. Like I showed you, methane, syngas production, from there only nitrogen is coming and hydrogen is coming. So the ammonia production has increased greatly. At the same time, these nitrates, KNO3 and so NaNO3, the nitrates, the resources are depleting. The nitrates resources are depleting. So the new route, the modern industry is following this route. To produce nitric acid, the modern industries are following the ammonia oxidation route. Modern industries are following the ammonia oxidation route. The reason is with the with the discovery of hydrocarbons, with the rapid invention of or rapid growth of petroleum refineries, the ammonia production rate also increased. Also, at the same time, the resources for KNO3 and sodium nitrate has greatly reducing, especially after World War II. So then they invented this reaction and following most of the current industries following this route, ammonia oxidation route. Just 1 second. Sorry, students. So the current industries follows this ammonia oxidation route. Let us see what is this ammonia oxidation route and what are the things we need to take care. Ammonia reacts with oxygen, produces nitric oxide NO and 6H2O. Ammonia oxidation, in the ammonia oxidation, ammonia reacts with oxygen and produces NO and water. Now, another important reaction also happens. Ammonia reacts with oxygen and produces nitrogen and water. Now you can see the Gibbs free energy for this is less than the Gibbs free energy for this. The Gibbs free energy for this is the nitrogen production reaction is lower than the nitric oxide NO production. So this is more favorable. This is more favorable than this. If you do the oxidation, if you do oxidation, simple oxidation reactor at any temperature, if you bring ammonia and if you bring oxygen comes in contact with these two, at any temperature, most likely what will form is nitrogen because this is more favorable than this one. The bottom reaction is more favorable than this one. So that is the trick. So what is the way we can avoid it? What is the way we can avoid this so that we wanted this one? What is the way we can avoid this so that we wanted this reaction? So if you wanted to alter the reaction pathway, there is only one possibility is by utilizing a catalyst. If you don't utilize catalyst, you're going to get nitrogen in the ammonia oxidation reaction. We are not going to get the nitric oxide. So if you want to make sure this reaction happen, so we need to alter the reaction pathway. We need to alter the reaction pathway. The only way we can alter the reaction pathway is by using the catalyst. So this is the typical required reactions. The reactions what we wanted to produce nitric acid is ammonia should react with oxygen and form nitric oxide. Then NO reacts with oxygen and produces NO2. The NO2 reacts with water and produces the HNO3. So these are the reactions we wanted. Whereas second reaction, third reaction are very simple. Very simple. So there is no major hassle in the second reaction. So here this is the as I showed you, this is the important reaction, nitric oxide. Now if you can see, all are exothermic reactions. Any oxidation, for that matter, any oxidation reaction is an exothermic reaction. So this is exothermic reaction, this is exothermic reaction. Now, and all are irreversible reactions. All are irreversible reactions. So we don't have any much problem with pressures. We don't need any high pressures. If it is only reversible reactions, to push the forward reaction better, we need high pressure. So we don't need any much high pressures here. That's what unless the catalytic reaction requires high pressure, we don't need to apply any much high pressures here. So these are the reactions, simple reactions. So whenever we have this reaction with water, that can be done in the absorption tower itself. Whenever we have water as one reactant, that reaction can always done in a simple absorption column. So let's see what is the way we can get nitric oxide rather than nitrogen is if you use platinum catalyst, if you use platinum catalyst, there is a this ammonia oxidizes into nitric oxide. If you don't use platinum catalyst, this is going to form nitrogen and 6s2. This is going to form nitrogen and H2. Just that is the important difference. Based on the equilibrium, the spontaneity of ammonia oxidation towards nitrogen is highly favorable. To alter the reaction pathway, the ammonia oxidation carried out in the presence of platinum catalyst. So platinum catalyst, and here this is very quick reaction. This is a very quick reaction, very short quick reaction. See, this is irreversible reactions, irreversible reaction. So it is always, as the temperature increases, the conversion increases. As the temperature increases, conversion increases, because there is no backward reaction. If you have a backward reaction, then as temperature increases, there is a backward reaction dominates, but that problem is not there. So we can use high temperatures and short residence time. We need to use shortest residence time. Now the platinum catalyst, you might know by this time, the platinum is very weak metal, mechanically very weak. The platinum is very mechanically very weak metal. So it always needs some support material. This always needs some support material. So rhodium is used as a support material. So rhodium support, this is a rhodium support, then they coat platinum layer. They coat platinum layer on top of this rhodium. Now, how to achieve this short residence time? How to achieve this short residence time? If this is in the form of particles, if this is in the form of particles, let's say you have a platinum the particles, the catalyst, if the catalysts are made as a particles, if catalysts are made as a particles, we cannot achieve short residence time because we have a tortuous path, we have a zigzag path. If you have a packed bed catalyst, we always have a tortuous path, zigzag path. Zigzag path means we cannot achieve the short residence time. If you keep it as a fluidized bed reactor, if you keep it as a fluidized bed reactor, the particles are flows, the particles are suspended, the particles are suspended. So when the particles are suspended, we can achieve short residence time. There is no problem with the short residence time. But still we cannot use fluidized bed reactors for this one. Can any student guess why we cannot use fluidized bed reactor if we have a platinum catalyst, platinum based catalyst? Any guess from the students? If I use catalyst particles as a fluidized bed, the platinum based catalysts are not suitable or not preferred to use as a fluidized bed reactor. Any guess from the students why we cannot use? Quick thought. What happens if the particles are fluidized? I will give a clue. I already gave a clue. The platinum is very weak, mechanically very weak. Please think about it. In case of packed bed, the particles are stationary, so there is no problem. But I am saying that when the particles tend to move, there is a problem. What problem could happen? Just think about it. Any answer from the students?
Pressure might be required more.
Pressure. If I put pressure, the fluidization velocity will be required more, no? If I put more pressure, the fluidization velocity will be more. So pressure is not a concern here. In the fluidization, can particles tend to hit each other? In fluidization, will particle tend to hit each other because one particle is moving, other particle is moving? Yes or no? One particle, another particle, this is moving and this is moving. Is there any chance of attrition between the particle? Is there any chance of attrition between the particles? High chance. In a fluidized bed reactor, there is a very high chance that the particle tend to hit each other. When particles tend to hit each other, what will happen? The layer of platinum usually comes out because even though you coat it, it is not very strong because it is interaction between platinum with any other metal is very less. So we cannot cross link. We can never cross link the platinum. We can only simply coat a small layer. So if I use fluidized bed reactor, because there's a high chance of iteration between the particles, whenever there's a iteration between the particles, there is a possibility of peeling off of the platinum material on the surface. We cannot use fluidized bed reactors. So we cannot use packed bed reactors. So what the only possibility, since it is a short residence time, they make mesh kind of thing. They make a mesh kind of thing. So the rhodium, the platinum coated rhodium made as a wires, small wires, and those wires are made as a mesh. They made as a mesh. See, this is the typical platinum coated rhodium catalyst. You can see they made like this. So if you arrange, so this is the reactor and this is the one layer of mesh, another layer of mesh, another layer of mesh. That way they'll make the multiple layers of the mesh. The mesh is nothing but the rhodium. The platinum coated rhodium made as a wires, and those wires are used to make the mesh, and that mesh is supported. So this way when the reactant gases flow over this, you can achieve very short residence because the pore size between this is very high. The gas can easily flow. Then only the residence time, short residence times can be achieved. The very short residence, very short means less than like in a few seconds. So that fast the reaction is. So that's why they made as a meshes. Also called as these meshes also called as gauzes. I don't know exactly proper way of pronunciation. So the gauzes. You can see gauze cloth. We say right whenever we have the bandage, whenever we want to apply the bandage, we have a gauze cloth. So they also made a typical the platinum coated rhodium wires made in this meshes or gauzes, and those will be used as a catalyst in the ammonia oxidation reaction. So that is the important feature of this ammonia oxidation reactor. One of the important feature of the ammonia oxidation reactor is that the catalyst platinum is coated on rhodium and made as a wires, and the wires is converted as a mesh, and that meshes will be used like a trace. So this is the typical ammonia oxidation reactor. This is the typical ammonia oxidation reactor looks like. So we have they supply feed. They supply feed from the top. They supply feed from the top. That is ammonia and oxygen is supplied from the top, and they're allowed to react it through this. They allow to react it through this meshes, the gauzes, through this one, and very fast. They supply very high flow rates, so that they will just pass through this gauges, and that way you will get the nitric oxide. Nitric oxide will come out from this ammonia oxidation reactor. Since this is exothermic reaction, lot of heat will be revelated, and since this is irreversible reaction, we don't need any intermediate cooling because at a higher temperature, higher the conversion. So we don't have to bother about the reducing the temperature. In the reversible reaction, we need intermediate cooling because high temperatures favors the backward reaction. So we need intermediate cooling. But whereas here we don't need any intermediate cooling. And also the water present here, the water present here will be in the vapor form because the temperature is very very high. So that we will get the nitric oxide and water vapor both comes out as a gases. Both comes out as a gases. So now, so that's what I talked about the first reaction. Ammonia reacts with oxygen and forms the nitric oxide and 6H2O. Now, the next one is nitric oxide reacts with oxygen and produces the NO2. Nitric oxide reacts with oxygen and produces the nitrogen dioxide, NO2. So here you can see this is non-catalytic reaction. Nitric oxide oxidation is a non-catalytic reaction. Non-catalytic reaction. Now, now one important feature we need to understand: NO2 reacts with oxygen and forms NO2. NO reacts with oxygen, forms NO2. There is one more possibility also possible, that is NO reacts with oxygen and forms N2O4. N2O4. This is also possible. Both are the possible. Now, if you see the equilibrium studies, at different temperatures, at a different pressures, equilibrium studies at different temperatures and different pressures, at low temperatures, you can see at the low temperature, N2O4 formation is higher. At low temperature, N2O4. See, this is the N2O4 curve. This is the N2O4 curve. N2O4 curve. At low temperatures, until 400 degrees centigrade, you can see at lower than 300, N2O4 is higher than NO2 content. At temperatures lower than 300 degrees centigrade, so 300 Kelvin, at temperatures lower than 300 Kelvin, N2O4 concentration is higher, and you can see here, this is NO2 concentration is lower. But when it crosses roughly 320 Kelvin, and NO2 dominates. But at temperatures close to 400 Kelvin, NO2 will be dominating. NO2 is very high and N2O4 is very very low. So that means this equilibrium data suggests that we need to carry out this process at temperatures between 400 to 500 Kelvin. 400 to 400 Kelvin. If you go beyond, again, if temperature increases, again N2O4 concentration increases. So whether at 1 bar pressure, whether at 10 bar pressure, the trend will be similar. But higher pressure, that will be shifted. At higher pressure, the temperature will be little bit shifted, but there is no other difference. Even at low pressure, at high pressure, same trend is observed. If increased pressure, the temperature will be slightly shifted to right hand side. So if you want to carry out the reaction at atmospheric pressure, then the preferable temperatures are between 400 to 500 Kelvin. So this is oxidation reaction and this is exothermic reaction. So although this is irreversible reaction, still we cannot run this at high temperatures. If we run at high temperatures, although there is no problem with conversion of this, but this reaction favors. The equilibrium study showed that this reaction favors. Now, one important concept I am highlighting in these last 4 classes is that whenever you design a reactor, whenever you design a reaction system, at what temperatures, what pressures we need to operate, it is totally depends upon the thermodynamic equilibrium and kinetics. So that's it's very very important. Thermodynamic equilibrium and the kinetics are very very important. So once you know the kinetics and thermodynamic equilibrium, we can pretty much tell that yes, this reactor has to be operated at this condition. So why we are operating at this pressure, at this temperature, entirely depends upon this thermodynamic equilibrium conditions. And how fast, how slow we can achieve, that is based on the kinetics. So these are very, very important concepts. So if I give some new reaction to you, and I say what temperature I should operate, then you should immediately find out what are all the different possible reactions can happen. Then if you do very simple, if you see chemical reaction equilibria in your thermodynamics chapter, if you take that one, there are very simple formulation. There are very simple formulations are there to find out this equilibrium conception. In CAPE course, I will also teach you using Aspen how to get this thermodynamic equilibrium data to study for different reactions. That I will teach in the second part of CAPE course. So once you know this, you know your reactor, what to be done for reactor, what is required, intermediate cooling required or not required, what is the metal thickness required, whether corrosion is important or not. So all these factors I am emphasizing so that you will, once you know this basic details, you should be able to tell quickly that yes, I need this, I don't need this, and all the factors you should be able to understand. Because because of the time constraints, I cannot cover all the process industries. I'm covering important process industries and I'm highlighting all the basic details so that if you take a new process industries, you should be able to easily understand all these basic details by yourself. That is what my aim. So from this uh, nitric oxide to NO2 and N2O4, this is the equilibrium data. So this is the typical process flow sheet. This is the typical process flow sheet of a nitric acid production process. This is the typical process of a nitric acid production process. So we get liquid ammonia from the ammonia process plant. Now, in this case, all are in the gaseous state. Ammonia in the gas, oxygen in the gas form. Then we get nitric oxide in the gas state. Then you also get the vapor state. Water vapor will come. So we have liquid ammonia. This has come from the ammonia plant, and that needs to be that all goes to evaporator because we wanted to convert gaseous form of ammonia. So this evaporator, it undergoes to the simple evaporator where the liquid is converted to vapor or gas. The liquid is converted to vapor or gas. Now sometimes this ammonia during the process, the liquid ammonia during compression or evaporation, it can contain some water droplets. Or oil droplets because compressors uses some oils. So sometimes water leak. So the water droplets can form. So those water droplets or oil droplets, or these are filtered. These are all filtered here. So we get ammonia vapors or ammonia gas. Similarly, we have air. Air is pumped. The air is compressed or pumped through this one. Then again heated to the required temperature because this favors at high temperature. So again heated to high temperature because the ammonia is coming at high temperature. The air also be at high temperature, and both enters the both enters the ammonia oxidation reaction. Ammonia oxidation reactor. As I said, it will be like a meshes or gauges of the platinum coated rhodium. Gauges or meshes are used, and spontaneous reaction happens on this catalyst surface, and this way you will get nitric oxide, and water vapors will come. And this is an highly exothermic reaction. So whereas this one needs to be operated at between these temperatures. This has to be operated at this temperature, right? Here the gases leaving the ammonia oxidation reaction will be at very high temperature because this is highly exothermic reaction. Minus 907 kilojoules per mole. And also to make it short residence time, they also operated very high temperatures, almost like 1200 Kelvin. They operated at 1200 Kelvin. So these are the reactor conditions. So this will be at very, very high temperature. So we need to cool down to 400 Kelvin because the next reaction, nitric oxide to oxide reactions favorable at 400 Kelvin. So we need to cool down. So they remove the heat. They remove the heat. This is boiler feed water, BFW, boiler feed water. So we have a coils, we have internal coils like heat exchangers. Through this coil, they supply water. The water is input and the heat is removed and you will get a steam outside. You will get a steam outside. And the steam goes to the, this steam goes to the wherever energy generation required or whenever, wherever different purposes this steam is used in the because usually this all industries connected, ammonia, nitric acid, all are connected into together with refineries. So this steam will be sent to the some other process. So although we cannot cool immediately, we cannot cool all the temperatures. So again, once again, we will have a boiler feed water is sent and it's converted to steam. So some of the amount of heat will be removed. Some of the heat will be removed. And still it undergoes to the condenser. Still it undergoes to the condenser. So that the finally will bring back to the temperatures around 400 to 500 Kelvin. I'm repeating, the nitric oxide comes out and water vapor comes out. It will be at very, very high temperature because it's exothermic reaction. So the heat is removed because the next reaction, nitric oxide reacts with oxygen and converts the nitrogen dioxide NO2. That should be operated at 400 to 500 Kelvin. So the temperature has to be reduced. That's why we have a series of heat exchangers are used. Series of heat exchangers used followed by condenser so that you will have the nitric oxide at very low temperature. Nitric oxide at the low temperature. So now you can see two important reactions. Nitric oxide reacts with oxygen and forms NO2. The produced NO2 reacts with water and produces HNO3. So often these two reactions done in the same place. These two, although we can do separately, but these two reactions can be done at same place. That way we can maintain that 400 to 500 Kelvin temperature easily. Here the condensed, here you can see it goes to this whatever nitric oxide comes here, just for time being, don't worry about this, I will explain. So the nitric oxide comes here and is supplied into this absorber. Now the air is introduced from the bottom. And the cold water is introduced from the top. So oxygen is introduced, air is introduced from the bottom, and from the middle NO2 is introduced. Now you say, why is this weak acid is formed? Because here we have NO and we have water. And since we are introducing air, some amount of oxygen also present. And this NO reacts with O2 and forms NO2. That NO2 reacts with water and forms HNO3. So, but that content will be very less. That percentage will be very less. That's why when you condense it, you will have some acid. And gases will be there. So you will have a weak acid and gases will be introduced into this absorption column, and air is introduced. The whatever remaining nitric oxide gases are there, that will be oxidized with the help of air here, and there will be a complete conversion of NO2 will happen. The NO2 reacts with water which is coming down in this absorption column and forms the nitric acid. That way you will get the nitric acid. nitric acid. So I am repeating, the NO and water vapor during the removing the heat, the NO can oxidize, some amount of NO can oxidize and react with water and form the nitric acid. So weak nitric acid and nitric oxide gases both are supplied into this absorption tower. Two things are fed into this absorption tower from the one from the bottom, that is air, one from the top, that is cold water. So whatever nitric oxide gases which are entering into this absorption tower reacts with oxygen in the air and forms NO2. Whatever NO2 which is produced reacts with cooling water which is coming from the top and forms the nitric acid. So nitric acid from here and nitric acid formed here, everything comes down as a final nitric acid product. Since we have the water is one of the water as a product here, water as product here, we will get the we will get the concentration vary from 65 to 70%. We will get the concentration varied from 65 to 70%. 65 to 70%. So that way we will get the 52 to 65% nitric acid concentrate. This much concentrated nitric acid we are able to produce using this ammonia oxidation process. So sorry, it's already 11 o'clock. I will just explain this one. Why are we using this in the next class? Apart from that, this is simple process industry or process flow to produce nitric acid. I hope you're able to understand, and I making you some or giving you some details which you are learning something. So with that, I stop here for today's class, and thank you very much. If you got any questions, please do not hesitate to ask me. Somebody's query. Oh yeah. So thank you, students. If you have any questions, please ask me. Otherwise, you may leave and join the next class. Please do not hesitate. If you got any questions, please ask me. I think someone unmuted and stopped. If you have questions, please ask me.